So good morning. This is Pete Alice from the National Fluid Power Association. Welcome to the FPIC Technology Conference, Minimizing Noise, Vibration, and Harshness in Fluid Power Systems. The conference is co-organized by MSOEs, Fluid Power Industrial Consortium, and the National Fluid Power Association. Over the course of the presentations, we're going to let people kind of go into the chat. You can network with others, but also use the Q&A button to ask questions of moderators and speakers. What we'll do, we talked to speakers yesterday in advance. They're going to look at spots where they can provide kind of a stopping point, ask for questions and things like that, and we'll monitor the Q&A area for questions. If there is one that's particularly timely, we might try to jump in and break in and ask that question. I'll be monitoring the Q&A to do that. The session today is being recorded. The recording will be available for download after the session. Usually it takes a little while for the recording to process and for us to have it ready probably early next week. But that will be available, and we will send an email to let people know when it is available. So really quickly, National Fluid Power Association, I know quite a few of you are members. We're a trade association representing more than 300 companies across the fluid power supply chain, manufacturers, distributors, suppliers, controls, IoT, and data companies as well. And go ahead, Paul.
No. Okay. So I'll just tell you a little bit about the Fluid Power Institute, basically, and the Fluid Power Industrial Consortium. First of all, I want to welcome everybody. Thank you for joining us today. Thank you to our speakers for coming in to help teach us about noise, harshness, and vibration in fluid power. So the idea here is that we're going to talk about market-ready solutions to reduce noise, harshness, and vibration in fluid power, and give you a little bit of educational background to understand today's topic. I want to share with you some news from the Fluid Power Institute. One exciting thing is that we're building an engineering center. The current Engineering Innovation Center construction has begun, and having the experience of hearing hydraulic equipment outside my window operating as they excavate that new facility that is going to help us to provide great experiential learning opportunities for students and also allow us to collaborate better with industry. Another exciting announcement is that we're starting a graduate certificate program in fluid power this semester. And so we're really happy to be supporting this educational goal of sending out students from the Milwaukee School of Engineering with specialized knowledge in fluid power. And then finally, we've got our Fluid Power Club just started up this semester, and we're looking for speakers. So please reach out to me if you'd like to talk to our Fluid Power Club. Today's presentation, attending it will allow you or qualify you for receiving continuing education or professional development hours certificates. So contact me and we'll provide you with a certificate for your timing. Our topic today is minimizing noise, vibration, and harshness in fluid power systems. Here's our schedule. So we're going to begin with Professor Sudhir Kaul, and he's going to talk about strategies for mitigating noise, vibration, and harshness. Then we're going to have Stefan Peterson talking about vibration testing in the automotive industry. Next, we'll have Nathan Pedigo talking about how to treat noise at the source with hydraulic noise suppressors. And finally, we'll finish up with Shanmukh Sarod talking about towards quieter hydraulic pump technologies. So I've got my notebook with me. I think there's a lot of good information that's going to be coming up here. It's a great learning opportunity for everybody, and I hope you enjoy today's presentations. Sudhir, please feel free.
Right. Thank you, Paul. Thank you for inviting me to present today. As Paul mentioned,
We're in presenter view here, Sudhir.
okay. Can you see my presentation or no?
We can see the next slide as well as the current slide.
Oh, sorry. Let me fix that here. How about now?
We're seeing two slides.
Two slides still.
Try to go back to the main
Yeah.
view. Go back to your main view, please, Sudhir.
Yeah. Just give me a minute here.
Sure.
Okay.
Sudhir, I think if you just bring it back up the way you had, and then there's that presenter mode at the bottom.
Yep.
Might be able to do that.
Okay, I think I have it back up. All right. Let's see if this works now. How about now?
No, sir. So if you look at the top, it says display setting in your current view on the, can you change that? Where it says display setting going up above the slide?
Yeah.
There, change that, swap or duplicate, either one. There you go. You got it.
Are you good now? Okay.
We're good now.
Okay. I'm using two screens here. That's why you were possibly seeing the other screen. Okay. Sorry about the couple of minutes here. Thank you, Paul, for inviting me to present today. I'm going to present a little bit as a generalist here on strategies for mitigating NVH. A little bit about my background. I serve as the chair of the Department of Mechanical Engineering at MSOE here. And my main research focus has been on motorcycle dynamics, modeling of motorcycle dynamics and ride comfort. So if a little bit of my presentation seems a little too general, non-specific to fluid power, I have tried to integrate a little bit of fluid power towards the end, but that's because my general background is in modeling ride comfort for motorcycle dynamics using vibration analysis.
Thank you, Sudhir.
I do have a stop right at maybe in the middle of my presentation where I will take any questions in between, and then we'll have another opportunity towards the end of the presentation for questions. So my overall outline today is I'll make some general introduction. I will classify systems and modeling approaches in terminology. I'll talk about vibration mitigation. That's a big chunk of the presentation today. I'll also talk about noise mitigation and noise mitigation strategies in general. And then I'll wrap up with topics associated with condition monitoring, structural or system health monitoring and diagnostics, which is rapidly emerging as a big application area for NVH. And finally, to address the audience directly today, because most of you are interested in fluid power, I will present a little bit about NVH and fluid power. I think it would be a good starting point for our subsequent presenters, because I feel like I will set the stage for our subsequent presenters who are more focused on fluid power. So first things first, NVH, widely used terminology, stands for noise, vibration, and harshness. Noise is any undesired sound, can be day-to-day terminology, and applications can manifest noise in different ways. Rattling, whining, etc. are all classified as noise. And it typically results from either a source, but also could result from many subsystem interactions, which is actually very pertinent to fluid power systems, because not only are we talking about the system itself, but many subsystem interactions as well. Vibration is repeating motion, or loosely called as shaking in day-to-day terminology, that is oftentimes intertwined with noise. Oftentimes, the source of vibration and noise could be very similar, but mitigation strategies can be significantly different for noise and vibration. Out of the three terms here, the one that is least quantitative is what's called as harshness. Generally, in automotive applications particularly, there is a jury evaluation that is done to understand the perception of vibration. And as a result of that, it's least quantitative and most qualitative out of the three terms we are talking about today. In day-to-day terminology, and depending on the kind of application we are looking at, terminology such as buzz, rattle, shake, chatter, whine, squeal, etc. are all some form of NVH that you will encounter from one application to another. So the most common models traditionally that have been used for evaluating vibration response and predicting noise response are dynamic models. Conventional models have typically been physics-based, but there is an increasing use of ensemble models that is being more and more used for many noise and vibration problems, because they allow us to go beyond physics models and address things like nonlinearity or interdisciplinarity between noise and vibration. A traditional physics-based model gives you a vibration model or a noise model, but ensemble models are allowing us to have an interdisciplinary model that does represent multiple things in the same model. The most prevalent use in ensemble models is of neural network algorithms, and that is being used to overcome some of the constraints that are typically posed by physics-based models. So I'll subsequently talk about the use of ensemble models a little bit more later in the presentation. And they're very useful and beneficial for diagnostics and condition monitoring that we'll also talk about later on in the presentation. In terms of classification, there are various different means and terminology that you may encounter when you're looking at NVH or NVH systems or classifications or subsystems. So I'll quickly go through some of the classifications here. The most traditional way to classify noise, vibration, harshness models is a single degree of freedom or a multiple degree of freedom system. In practical systems, it's very rare to encounter a single degree of freedom systems. Most practical systems are multiple degree of freedom systems. However, a single degree of freedom system is oftentimes the building block for multiple degree of freedom systems, or allows us to capture the essence of many systems as well. Likewise, it's very rare to see a system that is purely undamped, but many times using an undamped representation is very useful to understand characteristics of the system. And damping sometimes can be hard to model, That's why an idealized model sometimes is the starting point, which is an undamped system, and then you build damping on top of that. Another way of classifying systems is free vibration versus forced vibration. The next presenter is mostly focusing their talk on the use of test methods. Free vibration is very often used in test methods to characterize system dynamics, and forced vibration is typically used when you're looking at time to failure or number of cycles to failure in vibration diagnostics. Damping continues to remain an active area of research in any NVH study. The easiest one to model is viscous damping. Traditionally, the easiest one to model, and many fluid power systems particularly pertain to use of viscous damping. But hysteretic damping is also very common, so that's why these are the two most common form of damping that are used in NVH systems. Coulomb damping is also used. I have not listed that here. It's not as common as these two other form of damping. Another classification that is commonly used in NVH systems is proportional versus non-proportional damping. Proportional is easy to model because you're looking at a linear combination of inertia and stiffness to represent damping. But that said, there are many systems that manifest non-proportional damping, and it's relatively harder in terms of modeling, but many systems, non-proportional damping is also used. Last few classifications here, passive or active systems is one way to classify some NVH systems. Active systems are becoming more and more common in higher end applications. Passive is the most traditional use of noise vibration harshness mitigation, and we'll talk about both of them in the subsequent slides. In terms of analytical models, we generally deal in a time domain or frequency domain. And there is increasing use of what's called as the time frequency domain, which is a combination of time and frequency domain together. And finally, in terms of models, the classification is generally done as physics-based models, which is more traditional, or ensemble models, which is more recent development with use of neural networks or machine learning-based algorithms. And then finally, another classification in terms of modeling is linear or nonlinear. So we'll start with a couple of slides with the building blocks of the typical response and characteristics of a single degree of freedom system and multiple degree of freedom systems before we go to mitigation. So the bread and butter of a fundamental poor man's vibration model is a 1 degree of freedom spring mass damper model, shown here with the spring damper and mass or inertia of the system. And the typical response of a single degree of freedom system looks like this. In the modeling world, typically you start with this and get here. In the testing world, you start from here and reconstruct the model. Both are very commonly encountered in many applications and in many industries. The corresponding harmonic response of this single degree of freedom system, spring mass damper system, typically looks like this. These two look like very busy pictures, but the big picture to take out of here is that if we are in this kind of domain, the x-axis here is the frequency ratio, which is the excitation frequency divided by the natural frequency of the system. Then the damping ratio, which is the ratio between the damping constant and critical damping. As it increases, the response will reduce. The y-axis here is the amplitude ratio of the response to static response. However, the benefits start reducing once we go beyond a certain threshold. Increase of damping is not going to benefit us much, and increase of damping may also become very, very expensive, particularly in a passive system. So generally in applications where the frequency of interest happens to be in this region, a damping solution is provided where you choose a damping ratio and then adopt a vibration mitigation strategy corresponding to that damping ratio. This plot is not that significant, but nonetheless corresponds to the use and selection of the damping ratio. It's the corresponding phase angle where you go from an undamped system where the phase changes from 0 to 180. And then as the damping ratio increases, you go somewhere in between. It's not as drastic as 0 to 180. The phase angle is somewhere in between. The counterpart to the single degree of freedom system is a multiple degree of freedom system, 2, 3, 4, and so on and so forth. Here are two cartoon sketches of what a multiple degree of freedom system would look like. This system has 3 degrees of freedom, 3 lumped masses that are used to characterize the system. This is an automotive application where there are 2 degrees of freedom, bounce and pitch, which are coupled together. So this is a two degree of freedom system, which represents the planar dynamics of this system. Like the previous slide where we characterized the single degree of freedom system, here is a typical what a 2 degree of freedom system response, undamped response would look like. So the number of degrees of freedom correspondingly corresponds to the number of natural frequencies of the system. So in this case, the system has 2 natural frequencies. The system is undamped, so you see these infinite peaks here, which will start getting mitigated as we introduce damping into the system. And the second thing that becomes important in multiple degree of freedom systems is the corresponding mode shape of the system, which we don't see in a single degree of freedom system because there is no two modes you're looking at. You're only looking at one direction or one coordinate of the system. In the testing world, typically, you will test the system and gather the natural frequencies and then go back to the model, or do modal testing and then capture the mode shapes and then go back and build the model. In the modeling world, you will go the other way around, like we said in the previous slide. With that quick background, I want to talk about mitigation strategies for vibration. And I've listed the most common ones that are used. Some of them are more traditional. Some of them are modern and more non-traditional at this point in time. So we'll start with the simple passive vibration isolation. We'll talk about vibration absorption. We'll talk about damping solutions, a little intertwined with active vibration isolation and smart materials. So the last 2 are more modern, increasingly used in the last 15, 20 years. The passive vibration isolation solution basically is determining your frequency, operational frequency. The x-axis here is the frequency ratio. And then finding the damping solution which works in your region of interest. So in this case, the y-axis is the displacement transmissibility, which is the output to input displacement ratio. And the counterpart to this that you're looking at when you're looking at a passive vibration isolation solution is the force transmissibility. Just like displacement transmissibility, this is the output to input force ratios. So once you identify the frequency of your interest, if it happens to be below this threshold, then as you increase the damping ratio, you're mitigating or reducing the peak transmissibility, and you're also reducing the peak force transmissibility. However, there is a price to pay if your frequency range happens to be beyond this threshold. Increasing damping is actually going to increase the displacement transmissibility and significantly increase the force transmissibility, although the displacement transmissibility will still stay below 1. And in most physical systems, achieving very high damping ratios can be very expensive. So typically when you're looking at damping ratio solutions in passive isolation systems, you're looking at damping ratios of 0.2, 0.3, 0.4, and so on. A traditional passive isolation system would look like this, typically consisting of elastomeric elements, spring damper elements, and damping elements. Finally, just to see what an undamped versus damped system would look like, here is a simulation of a system which used to be rigid mounted. So this red line represents the response of the system, which is purely rigid mounted. And then with an engine mounted solution, a passive mounted solution, yields a new response where the peak, which you see here, has been significantly shifted from here to here. And if this is our frequency of operation, if this is the region we are mostly interested in, then the force transmissibility in this region has significantly been reduced. So that's a typical representation of what a passive vibration isolation solution looks like. There are many manufacturers that will provide you with a large catalog of parts that looks like this, or this, or this. So there's 4 or 5 big manufacturers. I have borrowed these figures from Trelleborg, which is one of the big manufacturers. But there are other manufacturers which will provide you with a catalog of parts and even help you identify a solution that works for you. If your production volume is large enough, you can even customize and pick and choose and build a mount or an elastomeric system, which is some combination of these. And you can develop that in conjunction, in collaboration with the mount manufacturer. The second solution in vibration mitigation is typically called that of vibration absorption. And a cartoon sketch rendering of that looks like this. So the system that we are looking at is a single degree of freedom system, which is isolated. So this is an isolated system. This is the single degree of freedom system. And this is what we are calling as the dynamic vibration absorber of the system, where we have added an inertia or mass or inertia with a stiffness and or a damper to the system to particularly target a single frequency of operation. The solution for this would look like this. So if the x-axis you're looking at is the frequency ratio, without the absorber, so without adding this entity, you're looking at a response which looks like this. If the frequency that you are interested in is in this range, then adding an absorber with this mass ratio shifts the frequency into 2 frequencies, one to the left, one to the right. However, the response in this particular range is significantly mitigated, as you can see here. The ironic thing here is, unfortunately, the terminology that is used in the industry is called as vibration absorption. Vibration is not really absorbed anywhere because you're not absorbing the energy anywhere. You're just adding a system and then moving the frequency response such that the frequency range that you are interested in sees a much smaller response as compared to the frequencies that you were primarily targeting. This is a very commonly used solution in machine tool applications where the frequency range is very narrow. Like I said, if the frequency range that you're interested in is right here, then this solution works very well because by adding this system, you have reduced the response in this range while increasing the response right before and right after. That said, this is an idealization because this was an undamped vibration absorber. A typical damped absorber response would look something like this, even though it's not as good as the idealized response looked like in the previous slide. But even despite that, in the frequency range that we are primarily interested in, which is right here, adding a damped vibration absorber still significantly reduces the vibration amplitude. So to summarize, the damped vibration absorber is a realistic representation of a viable solution for a vibration absorption system. A spring damper with an additional mass is what we are basically looking at as a practical way of adding the vibration absorber. Design decisions on tuning the absorber typically entail the selection of a mass, selection of the stiffness, and corresponding damping associated with that stiffness. And absorbers are relatively more common in stationary applications, or like I said, in machine tool applications where the frequency that you are interested in is very narrow. The counterpart to the last 2 mitigation solutions I talked about is use of smart materials and use of active vibration isolation. So I'll start with hydro mounts. Although hydro mounts don't by themselves classify as a smart material or an active vibration solution. They are a step in that direction. So hydro mounts offer a dual behavior, which is an augmentation of a typical passive elastomeric mount. And the dual behavior is generally a softer behavior at low amplitudes or high frequencies, and a stiffer behavior at high amplitudes or low frequencies. So it is an augmentation of the capability of a typical elastomeric mount because you're getting two characteristics using the same mount. And the main means of achieving this dual behavior is the use of what's called as a decoupler and an inertia track. More modern hydro mounts have actually seen the use of smart materials in conjunction with the hydro mounts. This is a typical cross-section of a hydro mount that I have borrowed from existing literature, where what you see, what dictates this duality of the behavior when you switch from softer to stiffer behavior is this decoupler and this inertia track, which gets opened and closed, thereby dictating the softer and stiffer behavior. This is a typical rendering of what a hydro mount would look like. I have taken it from one of the manufacturer catalogs. And the duality of the behavior, I have taken it from a simulation I ran a few years back for a hydro mount manufacturer, where you see the dynamic stiffness characteristics for high amplitude or low frequency input and low amplitude or high frequency input. The duality of the behavior is the dynamic stiffness changes with softer behavior and stiffer behavior. Further augmentation of hydro mounts or smart materials in general is the use of MR elastomers or magnetorheological elastomers, which allow variable stiffness and variable damping characteristics. The fluid itself has been used or has been in use for many damping applications for last maybe 25, 30 years, is a suspension of micron-sized magnetized particles that are dispersed in a carrier fluid with additives. But the MR elastomer itself, MRE, is a composite material that consists of the elastomeric matrix as the core matrix of the system, and then the MR particles are used as the filler material. So what that allows the MR elastomer to do is exhibit a typical viscoelastic property when there is no magnetic field, external magnetic field introduced. But when a magnetic field is introduced, you start seeing different behavior of the MR elastomer in that case. The behavior, luckily, is reversible, so can be controlled through an external magnetic field. The recipe of a typical MRE consists of, like I said, the matrix material, which is the elastomer itself, and the MR particles combined together. So a end product would look like a typical MR elastomer, a rubber pad, but it is a smart material because with the introduction of an external magnetic field, you will start seeing different properties of the storage modulus. Storage modulus, by the way, is a indirect measure of the stiffness of the system. The modeling aspect of MR elastomers is slightly more complex than a typical 1 degree or multiple degree of freedom system cartoon sketches I showed earlier. Nonetheless, it's more and more prevalent now, and even some manufacturers have started using MR elastomers or MR dampers in many high-end applications. I'll take a small break here and see if there are any questions before we proceed to noise mitigation.
No questions at the moment in the Q&A. Just as a reminder, if anybody has questions, please put them into the Q&A area. Looks like no questions.
Okay, so we will proceed with noise mitigation. And towards the end of noise mitigation, I may be able to capture the attention of the attendees a little more because I have some examples of fluid power systems. So as I mentioned earlier, while noise and vibration sources may often be intertwined, the mitigation strategies can be significantly different. The solutions that we are looking at for vibration mitigation may be very different from the solutions for noise mitigation. In fluid power systems particularly, I know that we have a subsequent speaker who may be addressing this directly. The pump is often the primary source of noise. So the design approach is either going after the source of noise or leaving the source alone if the solution is too expensive, then looking at alternative methods to mitigate noise. And the mitigation strategies could vary from fluid wave actuators or suppressors or silencers or attacking the root problem, which is design of the pump itself. Overall, in terms of transmission, particularly for fluid power systems, we are looking at different kinds of transmission. One is a fluid transmitted noise. We could have structural transmitted noise or air transmitted noise. And each one of these has different solutions, different mitigation strategies that will be used. I have borrowed from reference literature to kind of encapsulate the noise mitigation, particularly in the context of fluid power systems. And I think there are a couple of subsequent speakers who may talk about these in much more detail than I have captured here. In general, we'll break the mitigation into primary measures, which is this up top, and then secondary measures, which is the remaining. The primary measures get classified in terms of the measures that are taken to minimize pulsation or change pressure control or avoid cavitation. All of them called as primary because they're attacking the source of the noise, which is the pump and pump motor assembly and the design itself. The secondary measures can vary quite a bit, and there is a long range here. I won't read through all of that, but use of damping materials, avoiding airborne noise transmission by changing the working environment and so forth. So they fall into all of these categories, which can be drastically different from one application to another. What makes things more complex, particularly in fluid power applications, is because the fluid power system gets designed and then used in different applications. And the noise may result from interactions between several subsystems, making it even more challenging to have a universal design which can address all the noise mitigations. Furthermore, specific frequencies need to be targeted for noise mitigation. Hydraulic silencers I have seen in recent literature are often used to target those specific bands. And in addition to the system itself, the surrounding environment is very critical in the noise mitigation solution. So that's why there is no one solution that is applicable to all kinds of applications for fluid power systems or any other systems in general. A relatively recent offshoot of NVH is condition monitoring and system health monitoring. So the next couple of slides, I'll talk a little bit about the use of NVH for condition monitoring and SHM, which is the structural or system health monitoring. So condition monitoring typically entails the use of sensors and data collection, and it could be vibration related or non-vibration related. For example, collecting vibration, temperature, pressure data, etc., to reduce an unplanned stoppage or maintenance. So the governing principle here is that we want to collect data so that we can predict failure and prevent failure by intervening before failure happens. It's plays a critical role in enhancing productivity, improving safety, and scheduling preventive maintenance. The most common techniques that I have encountered related to NVH is acoustic emission, thermal imaging, and general vibration monitoring are very common for condition monitoring in general. The typical methodology is kind of encapsulated in a couple of figures I have shown here. Generally, we'll do some experimental design and some simulation modeling that ends up resulting in a database that is built to then diagnose the condition monitoring that one is targeting. Specifically looking at vibration testing data, the vibration data is collected and then fed through different kinds of models. Here I have borrowed a powertrain example, then fed into an ensemble model where you diagnose different kinds of failures. For example, a tooth failure, a surface wear, etc., are the different kind of predictions resulting from condition monitoring and ensemble modeling. There is an increasing use of deep learning in ensemble modeling. There's an increasing use of machine learning algorithms. And the development of ensemble models is happening in conjunction with the development of digital twins in some large complex applications where folks do have the data and the bandwidth to develop a digital twin of a large complex system. The use of SHM, structural health monitoring or system health monitoring more loosely, could be explained as an extension of condition monitoring, or in other words, CM is a subset of the overall system health monitoring or structural health monitoring of a system. SHM typically pertains to the continuous vibration data collection for large and complex systems. And the aim of data collection for SHM typically is much broader than just condition monitoring, where you are focused primarily on enhancing productivity or enhancing safety by intervening before failure happens. Augmenting physics-based models or developing ensemble models, building digital twins are all larger goals of SHM, which are in addition to just system maintenance and condition monitoring.
Sudhir, we do have a question.
Yes.
The question is, are the magnetostrictive damping response times fast enough to be used in vehicle suspension systems?
Yes and no. So if it is a typical damper that is used, the answer is that the response times are slightly longer, but we are talking about microseconds. But if it is integrated with the use of elastomers, the response time is much faster, because then you still have the fundamental damping and stiffness offered by the magnetorheological fluid in conjunction with the elastomer matrix that's being offered. So the answer is you may give up on a little bit of an increase in response time, but if you use the correct mix of strategies, maybe not that much. I have seen the use of, in some cases, feed-forward algorithms where the response time has been reduced as well by simply using MR dampers. Did I answer the question? I can also point folks to references which talk a lot more about both MR elastomers, MREs, and then MR dampers by themselves as well.
Thanks, Sudhir. I don't see any further questions.
Okay. So next few slides of NVH in fluid power. I hope that excites folks a little more than the rest of the previous presentation. So I'll talk a little more about the use of NVH in fluid power in different ways, and I hope that this is a good building block for subsequent presenters who will talk in a lot more depth on fluid power. So the pressure and flow demands in fluid power applications can vary significantly, as most of you may know much more than me. Independent metering solutions have been increasingly used to reduce energy consumption in many fluid power applications. Although they may reduce energy consumption, they do end up giving us a little bit of a penalty in lower damping and therefore increased vibration. So when I talk about independent metering, this is what a typical sketch looks like. I have borrowed these sketches from a couple of references, which I have listed at the end of the presentation, so folks can look at this in more detail by themselves as well. And the typical gain between the traditional system and an independent metering system like this is, like I said, the big gain is saved energy. However, the small price to pay is lower damping, therefore higher vibrations in these cases. There are multiple solutions of enhancing damping in fluid power systems. I'll quickly show a few examples here and we'll talk through all of them. So I picked 4 from a couple of references I was looking at. Let's start with the most basic one, which is physically adding damping here, which you see right here. So physically adding damping in the system to enhance the overall damping of the system. Another possible means of achieving the same without adding physical damping like we did in this case is the use of an accumulator, which I know is common in some fluid power applications. But there are even other options like using the positive opening valve, which is shown here, or using a bypass valve, which is shown here. There is no slam dunk here. All of these come with pros and cons, with response time, increased cost, complexity, and so on and so forth. In fluid power applications, based on what I have seen in most of the recent literature, acceleration feedback or pressure feedback provides additional means of control that can be used for enhanced damping in most systems and most applications. The hybrid methods that combine pressure feedback with active damping do demonstrate a very high amount of vibration mitigation in many applications in fluid power. And finally, in mobile hydraulic applications, the complexity of mitigation is even more because there are intertwined considerations associated with machine life, the application that you're designing for, operator comfort, safety, etc. There was this table that I found in one of the recent references that I think encapsulates things in a very concise manner, and I'll show this table. This is the source I borrowed it from, which shows the range of frequencies and the corresponding effects associated with the frequencies as well as the noise measured and the amount of exposure. The N here stands for the number of data points that have been used to come to these conclusions. The summary of this table, which you can see for yourself, is that the infrasonic noise, which is typically associated with 1 to 20 hertz, has behavioral and health implications. It's kind of the core of why one wants to address a noise or why one wants to mitigate noise. The length of exposure and combination of vibrational frequency and acoustic pressure levels, which is right here, play a critical role. So oftentimes it's not just the amount of the acoustic pressure level, it's also in conjunction with the time of exposure that leads to specific symptoms associated with the influence of noise. Finally, as I mentioned before as well, design changes, material selection, damping, environmental design, protective gear are all possible means of mitigation, particularly for noise. I know we are running out of time. I would like to take a minute to brag about some of the things at MSOE and to repeat what Paul already mentioned. We have a recognized Fluid Power Institute at MSOE. We have a recently added graduate certificate program. We also do multiple projects through FPI, which with a FPI staff and a faculty supervision. We have senior design projects, so undergraduate research projects, or independent study projects that we execute here at MSOE. And we have multiple research projects with FPI and MSOE faculty as well. I want to thank the references that I have borrowed from, and if the presentation is made available to all the attendees, you will see all the references for yourself. Thank you for your attention, and I can take a few questions if there are any questions.
We do have a question in the chat. The question is the placement or location of a damper or isolator within an assembly important? Are there any basic guidelines you could share?
Absolutely. Absolutely. The location is important, and so is the model itself. So if we are looking at a simple 1 degree of freedom model, then the location is neutral because you're not looking at specific orientation and location. But there are many, many papers which talk about optimization of location and orientation of the mounting systems that become very important in any multiple degree of freedom system. Absolutely. I can share even my own papers if anyone is interested.
Thank you, Sudhir. I don't see any other questions. Paul, you want to take over?
Sure, excellent. Well, thank you very much, Sudhir. And yes,
Thank you.
Appreciate your presentation, and the information you share is very helpful. Next, I would like to introduce Stefan Peterson. He's a staff applications engineer at MTS Systems Corporation. He's going to be talking about vibration testing in the automotive industry, and that'll provide us with an excellent benchmark for what we can use to gauge what we understand would be applicable for the fluid power industry. So Stefan brings over 24 years of experience in the automotive industry, including 5 years as a test engineer at Harley-Davidson and 19 years at MTS Systems Corporation. Throughout his tenure at MTS, Stefan has held several key roles, including regional service manager, project manager, and staff applications engineer. Since 2015, he has also been leading the development of MAST, that's the multi-axis simulation table solutions, tailored to evolving customer and market needs. His deep technical expertise and customer-focused approach have made him a trusted partner in delivering innovative and effective testing solutions across a wide range of applications. Stefan, can you please load your presentation? Share your presentation.
Yes, I will. So thank you for the introduction here. Can you hear me? Good?
Yes, we can.
Very good. So I make sure here that I get started. Let me see, there it is. Now it's back there. Show caption. So, can I ask you something? Yes. Oh, now I see it's green. Perfect.
Starting to share.
So that you should be able to see my presentation, right?
Yes.
So welcome everybody, and thank you to the presenter before me, because I think this will be a follow-up to what he was talking about as well, and give you some ideas how customers are actually testing products in vibration systems. So I already had a nice introduction here, so I will continue to explain a little bit what I'm going to talk about today. First, I will give you a little background about MTS if you don't know about who we are. A little bit about what our components are testing on our vibration systems, and then a very high level about vibration testing and example of test solutions. And in the end, I have 3 real-world applications, how customers are using our system to solve different issues. Here we have battery pack testing for vehicles, and also fuel tank testing and fuel slosh systems. It may not be directly applicable to what some of you are here for, but it can give you ideas of components that are part of any fluid analysis in a laboratory. So a little bit about MTS. There's a link here in the top, and you can this presentation will be shared as well, so you can learn more about us there. But we are located in Minnesota. We have affiliates in Sweden, England, Germany, Italy, France, India, China, Japan, and Korea. We also work with business partners. We were founded in 1966, and we were acquired by Illinois Toolworks, ITW, in 2021. So what is MTS doing? We are providing hydraulic and electric test equipment solutions and services globally. We have 4 business units. We have ground vehicles. GRV it's short for ground vehicles. Here we work with customers providing passenger cars, light truck, heavy truck, rail, Formula 1 racing, motorcycles, ATV, etc. And we work with OEMs contract test labs, sub-suppliers, and even universities. The next business unit is materials. We also do structures and aero and service and aftermarket. So materials, there you're looking more into kind of strengths of materials, small specimens for understand every properties of a material. Structures and aero, structures are mainly, I would say, doing earthquake testing, primarily for medical equipment, but also for buildings. We also work with aero customers that are designing and manufacturing airplanes. And the key also our business is our service and aftermarket products. So we don't do any testing ourselves. We provide solutions for our customers. So I highlighted the ground vehicles here, or GRV. That's the business unit that I belong to. So what do our customers test in the GRV? I'm also touching on some other markets that are actually using the solutions that I'm responsible for. Currently, market drivers are around electric battery development and electric vehicles, for both battery electric vehicles and plug-in electric vehicles. But every single component of a vehicle can be tested on the vibration system. Powertrain mounts, fuel tanks, radiators, seats, electric systems, instrument panels, exhaust system. We also comment on seismic application here that are would be in the vibration, would be earthquake systems, but also transportation and packaging standards. For seats, we also see a lot of more requests for seat testing. That has to do with again, electric vehicle development, that vehicles are getting heavier and that components part of the vehicles, such as suspension and dampers, are changing as well. So we're getting a lot of requests from customers again to work with ride comfort and transmissibility, but we're also getting requests for human rated test systems where we actually would have a human in the test space. So that's pretty much any component part of a vehicle we can most likely test. So general about vibration testing, we see customers are executing durability test, NVH test, or performance test. I will provide more details about that in a little bit. But these tests are either uniaxial or multi-axial, as the former speaker were mentioning as well. So durability testing, here you're reproducing acceleration and time histories or power speckle densities, the environment that the test object is exposed to. These tests are usually run to failure or for the duration of its expected life. Noise and vibration testing are typically lower amplitude tests, can be a combination of time history and sine sweeps. And here we can also integrate our vibration system into an anechoic chamber. Performance evaluation is kind of a combination of durability and other effects. So here we can again see transmissibility as ride comfort, human in test space, but also aging. So we can install our system in temperature chambers or environmental chambers and expose the specimen or the test object to both temperature, humidity, solar, such as heat load. So talking about testing requirements. So it's important to understand how the component is exposed to vibration. There are different ways to define what requirements really are. The most common one for GRV is that a customer owns a customer correlated proving ground, or that they rent time at the public one. The picture here to the right is the proving ground for General Motors in Michigan. And with a customer correlated proving ground, the vehicle will drive around this proving ground for example, about 6 months. And after 6 months, the life of the vehicle would be accounted for. But there's also test standards. There are ISO standard, SAE standards the customer is using, and customers also using computer analysis and simulation, part of defining testing requirements or test profiles. So when you understand what the system is exposed to, so coming back to the customer correlated proving ground here, they're using accelerometers and strain gauges, for example, and here they can identify vibrations that are induced from the road, and they can also identify vibrations that are induced from the engine, and how those vibrations are transferred within the vehicle as well. So when you're doing this analysis, these are deriving in uniaxial or single degree of freedom or multi-axial degree of freedom as vibration tests. So most tests that our customers are doing are multi-degree of freedom vibration tests. So here in phase, multi-degree of freedom is necessary to validate the durability life of components and subsystems. But while you're testing, it's very, very important also to understand what the fixturing and boundary conditions. If the fixture and boundary conditions are not correct, the testing will not be valid. They will also need to understand the environmental aspects. Are there any temperature that needs to be accounted for in the testing, and similar? So this is usually from this analysis. This will drive requirements for testing, and depending on the size of the specimen, the mass of the specimen, this will also determine the control band frequency they have to test. So why do customers perform single degree of freedom or multi-degree of freedom tests? It's to ensure the quality of the component or vehicle and reduce warranty expenses. So there are many advantages of testing in a test laboratory compared to running a vehicle on that customer correlated proving ground. It increases the consistency and repeatability of the test input and test results. It shortens the vehicle development cycle. Tests can be accelerated by eliminating non-damaging content. Tests can be executed on the component level before a full vehicle is available. It will also minimize delays due to weather. And another important aspect, it reduces human injuries when driving on proving grounds. So coming back to this proving ground, that was how customers developed, tested their vehicles in the past. Here they ran 2 shifts per day, and for about 6 months to validate the life of a vehicle or a component. So I can make a break here and ask if there are any questions. So I don't think there are any questions.
No questions at the moment.
Okay, so here you see some example of test solutions that are sized for in this case table size or mounting surface. Also for mass, we will size an actuator for the specific specimen and for the control band frequency. So So what you see to the left here is a uniaxial system that is vertical. It's a hydraulic test system. It's from MTS. What you see in the middle is a electrodynamic shaker system. There are many benefits with both hydraulic test equipment and electrodynamic test equipment. MTS doesn't provide any electric dynamic test equipment like you see in the middle here, but they're frequently used in uniaxial test systems. And here you can reach frequencies that are much greater than you can do with the hydraulic test system. The system you see to the left there, you can probably test up to 100 or 200 hertz. The systems in the middle, you can probably reach control band frequency up to 2000 hertz or more. The picture to the right is a mass system. It's a multi-axial simulation test systems. We have different sizes at MTS, and I will just review a few of them so you can get different ranges. But here the smallest system we have can test up to 500 hertz in 6 degrees of freedom. So the first mass system that MTS delivered was in 1989. That's what we would call the first standard system. But since then, we have over 230 systems installation. And since I joined working on this project in 2011, had a different role in 2011, but we have delivered over 120. And this is also how MTS has grown into emerging market. And we had a big growth around 2011 and 2012 in China and Asia. And it's still growing, and now mainly because of electric vehicles. So here you see kind of our standard test portfolio. We're going from small to large. The smallest one is a 1 meter round table. We can test specimens up to 500 hertz, and resonance-free control bandwidth up to 500 hertz, but we can actually in uniaxial testing we can test this one up to 900 hertz. It's for both durability and with the NVH application, and they can be integrated with both environmental chambers and anechoic chambers. The next system, our 35320, has a larger table. We can put heavier specimens on the system, but here we get, because the table is larger and you have to support the table with actuators to transfer the force into accelerations, the control band frequency is reduced. The resonance-free control bandwidth is 150 hertz, but uniaxial we can test up to 200 hertz. Here we have, it's mainly used for durability applications, but also for ride comfort applications. And we can integrate this system as well with environmental chambers and anechoic chambers. The next system is our 5350. It has an even larger table and heavier payload, but here the frequency is sacrificed by the larger table. It's more for heavy duty and off-road application, and also for seismic application of larger earthquake systems. The last model that we developed was in 2015. It was our 35320. It's very similar to the 35320. Table size is identical, but here we have higher payloads, but we're using a different actuator technology here. So before I continue, I want to make another stop because I will come into I have 3 real-world applications before I'm done, and wanted to step back here and ask if there's any questions again.
I don't see any in the Q&A, but I just noticed in the chat a question about, can you speak about ISO or SAE standards for NVH testing of ground vehicles or components?
Yeah, so there are squeak and rattle, right? Was that the question?
Speak about ISO or SAE standards for NVH testing of ground vehicles or components.
Okay, I don't have any directly with me today. So there are an ISO standard here in this real world application of battery pack testing. I can comment on. It's not directly an NVH, but there are many seat standards, for example, that we do follow, and there are more, what I would say, related to that. But if you have any questions, I can follow up with that after the meeting or the presentation. So
Okay, I don't see any other questions.
Okay, very good. So I talked earlier about market drivers for MTS currently and what's happening on the market, and one big thing here is battery pack testing. Every single OEM has a program to provide a fully electric or hybrid vehicle. So customers are testing battery pack testing, and in the last 5 years, we have 5-6 years, we have about 24 installations, I think, where we're providing solutions for battery pack testing together with other suppliers. So what we also see on the market is that the OEMs are seeing a high increase in warranty cost. So it's important for them to test. So they are testing really here for durability and performance, for error in the design, thermal management, mainly software, and manufacturing issues. So the most common standard that customers use is ISO 12405. It's pretty flexible standard. The customer can decide, or the OEM can decide if they want to run PSD testing, power spectral density testing. Those are all uniaxial, so there's no correlation in that standard for between the axes. So it would be that they run the test first in X, and then in Y, and then in C. But it's also flexible, the standard, that they can actually use the customer correlated proving ground to run a 6-degree freedom test, and that's what most of our customers are doing. So the test standard is defined by the battery cycling charge and discharge profiles, and part of this, they are doing the 6-degree of freedom vibration, and so the battery cycler that charging and discharge the system would trigger our vibration systems to start vibration and stop vibrations. Part of this, the battery cycler will also command or trigger temperature to change. So they will do ramps and hold of different temperatures. And they're doing this mainly in the top here, you can see that I say it's both durability and performance. So they want to make sure that their battery packs are durable, but the key here is also the performance of the thermal management, because that's a high warranty cost that they see right now. So I have a video showing how a test system is set up here, so you can see that. So this is a video courtesy of CTAG in Spain. It's an agricultural battery. The tractor in this case would have 2 of these battery packs that you see here. And part of this testing, you see here, you don't only see vibrating essentially, but the whole system is installed in a temperature chamber where they can expose to temperature, humidity, and also solar. Okay, did we have any more questions in the chat, or is it?
No questions right now.
Okay, very good. So I have 2 more real world applications so that will show what how the customers are using it. So this is the next one here is a real world application of a fuel tank testing. So durability performance. So this was the combined test. There was the straps holding the fuel tanks into a heavy truck frame, but they're also making sure that the fuel tank sensors inside the tank would survive the whole durability life of the test and being accurate. So in this case, the test was defined by test profile from the customer correlated proving ground, and this was 6 degree of freedom. The specimen in this case was 2.5 tons, including fixtures. So this is a test fixture that the customer built. Here's the truck frame. Here's the fuel tank. And they were validating this, the straps holding it. So they were failing the straps on the field, and this system helped them to solve that. And they had no issues with the straps after this. So I have one more here. See if there's any more questions or in the chat or not. So the last one here is a fuselage test for an airplane application. I can't show a picture here because I don't have the permission from the customer to do so, but I can at least show the system and give you an idea that how they tested this one. So again, it was both a durability and performance test. I would say it was more a performance test than durability, but it's looking at the fuel tank sensors in an airplane wing. And in this case, they had 105 sensors that was monitored consistently during the test. And the idea here was for them to test, make sure that the sensors were functional at all time. They had redundant sensors too, of course, but with different fuel levels in the airplane wing. So the test was defined by the airplane wing motions, landing, takeoff, etc. And there was a 2 degree of freedom vibration airplane test. Here we control the system into a roll and pitch, and the profile for sinusoidal or triangle form. So here you can see the system. The airplane is taken off in this case, very steep. And then the next event here will do a dip down as they're doing it. So it doesn't look so dynamic as the other one, but it's so the idea here was really to test to make sure that the sensors inside the airplane wing was functional at all time. So I think that's pretty much what I had for today. I can definitely follow up with some ISO standards for NVH testing. The majority of what our customers do is a durability test, and when they do NVH application, they're mainly listening to, for example, dashboards. They're listening to seats. They are listening to doors, for example, because they want to minimize the sound inside the vehicles to make it as comfortable as possible for it. So the only standards I've really seen around it for other applications are around seat testing.
Stefan, this is Pete. I see there were a couple of questions that were put into the chat. Let me give you some of these. One of them is, how are the test machines actuated? Do you find this to be a limitation to create an equivalent vibration profile to what you see in the proving grounds?
So coming back to one of my first slides, not the first slides, but so when you're moving from the proving ground into a test, the fixture and boundary conditions are critical, and it's very challenging for customers. If you're looking at this battery pack testing, for example, they're doing here, we have a stiff table, and this is a pretty condensed design of a battery pack because it's agricultural. But if it would be a car battery pack, it will be more distributed and will be part of the structure of the vehicle. So on a mass system, it can be very, very challenging to see all the modes of the battery, because you can't induce any twisting and bending modes. There are solutions for it, but it's also increased the complexity of the system when doing that. So it's definitely a challenge to move from the proving ground into a test environment.
Okay, thank you. Another question. How important is it to also take into account rotational accelerations?
So I would say it's critical, but the minimum, as I see it, would be 3 degrees of freedom. That's usually what you see. So if you're thinking about a battery pack again, I'll stop this video. There are rotational accelerations around X, Y, and Z, and we are trying to provide those as well. In the real world application, there are rotations there, so they should be considered. But on some mass systems, that's very difficult to do because of the stiff tables. So the larger a specimen becomes, the more difficult it is to get the real right boundary condition. In that case, you have to do a full vehicle test. We have solutions for full vehicle as well, but usually those are reduced in frequency up to 50 or 70 hertz. Most test standards for battery testing are asking for 200 hertz or more. So that's and they are mainly a lot of them are written also for electrodynamic shaker testing, but also are uniaxial, and then they're missing off another of that uniaxial are not as accurate as multi-degree of freedom test, and they will still have the same issue with boundary conditions.
Okay, thank you, Stefan. I see no other questions. Thank you very much, Stefan. Paul, do you want to tee up the next presentation?
Thank you.
Okay. Next up is Nathan Pedigo from Wilkes & McLean. He's going to talk about treating noise at the source with hydraulic noise suppressors. Nathan is the head of engineering at Wilkes & McLean and has almost 10 years of experience in the field of hydraulic noise control. Prior to joining Wilkes & McLean, he performed research in passive noise suppression in hydraulic systems, water hammer mitigation, and transducer response characterization. Mr. Pedigo previously worked at Sun Hydraulics in the fields of cartridge valve design and manufacturing engineering. He has also had experience in acoustic consulting for legal action and environment and entertainment venues. Mr. Pedigo received his Master's of Science in Mechanical Engineering with a focus on acoustics from Georgia Tech in 2017. Happy to introduce Nathan.
All right, thank you, Paul. So as Paul indicated, today I'm going to be discussing hydraulic noise suppressors and how they can be used as a really critical component in a noise abatement plan for any hydraulic system. Before we get started on the presentation in earnest, I kind of wanted to introduce my company. So Wilkes McLean is a relatively small company based out of the Chicago area, and we have about 40 years of experience with both accumulators and suppressors. So under our Wilkes Pulse brand, we manufacture the world's most really the world's most popular hydraulic noise suppressor, and we also manufacture the only true maintenance-free hydraulic noise suppressor. Under our Wilkes Accu brand, we rep NACOL accumulators, which have a number of really unique design features that make them extremely reliable. And our suppressors are going to be the focus of this presentation, but if you do ever need a quote for an accumulator, you can definitely reach out. We'd be glad to quote you for that. And just a little bit about where this presentation is going to be going. First, I'm going to run through the basics of some really kind of core principles to noise control engineering as a field. I'm then going to discuss how our suppressors actually work, and then I'm going to present a few case studies. At the end of each of these sections, I'll take a brief break for some questions. All right, so noise control engineers usually think about noise in terms of quantity and quality. So it's kind of like Sudhir mentioned earlier during his presentation. The quantity that's going to be the actual volume of the noise. And when I say noise, I'm thinking about it in a much more broad terms. So, whether or not it's in like vibration or if it's in oil or if it's in air, it's all acoustic energy. So to me, it's all noise. But in the air, you have the risk of creating hearing loss if the intensity or power is too high. And it can also cause disruptions to communications, which can be very dangerous on job sites. The quality is going to be the subjective impression of the noise. So this is where you get into things like harshness and different psychological factors. So things like, nails on a chalkboard, everyone really hates that. It's because it has certain characteristics to the noise that are particularly grating to humans. So we would also think about that. It's usually kind of a secondary issue for noise control engineers, but it's not always. And even some, local, state, and federal regulations do take into account those kinds of psychological factors. So as I mentioned, no matter what the medium is, I just think about it as noise, but there are a lot of different words for what you might call noise in each of these systems or each of these media. So fluid-borne noise is usually going to be called pulsation or pressure ripple by our customers when they contact us. And then structural noise is usually talked about in terms of vibration or shaking. It's also important to note that fluid-borne noise and structural noise are very interrelated because the stiffness of those two medias are actually pretty comparable. So there is a lot of interaction between vibration and the noise in a pipe. And then airborne noise, most people will just call this noise. Some noise control engineers will call it breakout noise just to differentiate it from the other types of noise in a system. And again, there is a coupling between like the structure and an airborne noise for a hydraulic system. We don't usually consider the path of the air to structure sound, or sorry, air to structure noise path for that energy because the energy is just way, way lower in airborne noise. For reference, you're usually talking about something on the order of microwatts for airborne noise, and for structural and fluid-borne noise, you're talking tens, hundreds, even kilowatts. So the next concept I wanted to discuss for noise control engineering is the source path receiver model. Um, Basically, the concept here is that you have places where you can work and places where it's better to work than others. So I'm going to discuss this a little bit for kind of a standard hydraulic system, nothing too complicated. So you'll have your motor and your pump. Those are going to be coupled, so those are going to be shaking like mad, and also they put out energy into, the surroundings. So the motor will often have directly contributing to breakout noise through things like a fan on the motor to cool it down. And the pump is usually directly coupled to all of your piping systems. So that's going to contribute directly to the structural noise. But in addition to that, every single pump that's ever been made will introduce some amount of noise. Doesn't matter if it's a rotor, gear, piston, or vane pump. They all produce noise in the fluid itself, and that noise in the fluid will, be transmitted throughout your system. So if you have things like vibration isolation mounts and enclosures, you know, the fluid-borne noise is not going to be at all impacted by that. And then that fluid-borne noise goes back into your structure and it, reintroduces that acoustic energy elsewhere throughout your system. So this contributes to the breakout noise a little bit indirectly, but in a very strong way. And then you have your receiver. So basically, as soon as you created noise, you will have the receiver noticing it. And this is not super critical all the time, but sometimes it very much can be. And a lot of times in hydraulics, it is. I'm sure everyone that's in this has been, in this seminar has been in a pump room that's been just quite frankly unbearable. So NCEs try to intervene as early as possible in that source path receiver model. This is because the noise hasn't been amplified yet. So basically, our intervention can be a lot smaller. And because it can be a lot smaller, it's dealing with a lot less energy. It's typically going to be less costly. So the other thing that's kind of critical here is people really do tend to disregard the risk to their hearing. I can think of, just everyone that I see on a day-to-day basis with earbuds in that's just blasting the music to where I can hear it passing them on the sidewalk. Those people, it's not painful to them, but they're probably listening to this music at a level that's going to be actually damaging to their hearing in the long term. And if you're not going to get those kind of acute hearing impacts, most people just kind of think that, oh, I'm safe, so they won't do things like wear hearing protection. So suppressors really do prevent that transmission of the fluid-borne noise throughout the system. And we always tell our customers to install the suppressor as close as possible to the noise source. In a lot of places or a lot of systems, it's going to be the pump. And this is just because it really mitigates the risk of that, you're going to have structural noise later on that's going to cause breakout noise. And also being as close as possible to the pump, you're limiting the amount of area where you're going to have a kind of increased amount of acoustic energy being able to break out. And multiple types of interventions are necessary for most hydraulic systems. As I've indicated a couple of times, almost everyone will have their HPU on like vibration isolation pads. That prevents the ground from shaking, or if they're on like the second floor, it prevents the whole floor from becoming a bit of a speaker. Um, and then also things like enclosures are very common. Even a submerged pump, that's really kind of an enclosure from an acoustic perspective because you're putting that pump inside of the tank, preventing more of that acoustic energy from being transmitted. All right, are there any questions before I move on?
No questions in the chat. No questions in the Q&A right now.
All right, so I'm going to go ahead and move on. So in a suppressor, or you'll also often hear things about like expansion chamber mufflers. These all work basically the same way. There's three fluid layers, and these layers are going to be defined by their characteristic acoustic impedance. Basically, that's just a property of the fluid and pipe selection that I'm going to discuss in just a little bit more detail in a couple of minutes. But when you have an incident pressure wave, so you have sound coming in, when you hit that second region with a different characteristic acoustic impedance, you're going to have a transmitted and a reflected wave. The transmitted wave is going to be of lower energy than the incident wave. And again, that reflected wave, that's basically carrying the rest of the energy back towards the source. Again, this is why we recommend people install them as close as possible, because you will have a small region where you're going to have more acoustic energy. But if you can, if it's mounted right next to the pump, well, then you're basically not going to really increase the amount of vibration in the pump just by doing that just by that small amount of acoustic energy there. So the characteristic acoustic impedance is related to the density, speed of sound, and cross-sectional area of each region. So in our diagram above, zones 1 and 3 are basically, for most hydraulics systems, going to be the same, because no one really wants to change the size of the pipe just kind of midway through a span. So that cross-sectional area on 1 and 3 are basically decided by whatever line size our customers have. We decide the cross-sectional area of zone 2, but that only can get you so far unless you get to very large expansion chamber mufflers. They tend to not be highly effective for hydraulics for a variety of reasons. And the speed of sound method of modeling the characteristic acoustic impedance isn't always necessarily the kind of ideal, because it's really usually kind of hard to directly model that speed of sound, because it can be actually different for different frequencies. And for that reason, we usually talk about it in terms of the bulk modulus that's in that cavity. And the way that our suppressors work, which differentiates them from expansion chamber mufflers, is we directly alter the bulk modulus and the density in that cavity. One other thing to point out, the bigger the difference in the characteristic acoustic impedance from zones 1 to 2, the more effective the suppressor is going to be. So this is a cutaway of one of our bladder style suppressors. The bladder clamp, shell, and charging valve here are really not particularly critical for the acoustic side of things, but they allow us to interact, basically to interface with whatever system you have, withstand the pressure, and then also allows us access to charge the suppressor. The bladder and nitrogen and diffuser are the kind of critical acoustic components. So that bladder and retaining that kind of annular section of nitrogen, that's what's going to actually alter the bulk modulus within the suppressor. And then the diffuser is there for structural reasons when you have your hydraulics turned off, to make sure the bladder doesn't, basically rip out of the suppressor. And also it will give you some kind of higher frequency attenuation, because it'll create a little bit of a tortuous path for certain sound. So as I said, the nitrogen is trapped by the bladder, and again, just thinking about it in terms of the bulk modulus and density rather than the density and speed of sound. The bulk modulus can be found in a way that's pretty analogous to like springs in series, but you volume weight it based on the volume of what they occupy inside the cavity. Similarly for the density, it's just going to be the volume weighted density within the cavity. And these are going to be effective numbers. So it's not really like a high resolution kind of modeling that I'm talking about here. It's pretty basic. It's just to get you the idea, because really getting into the nitty gritty of all that can take weeks or months to really understand. So these bladder style suppressors, they're really, really highly effective for being that size. So they'll reduce noise by up to 30 dB from 50 hertz to 5,000 hertz, and that's the noise in the oil. It's harder to talk about the noise in the air, but we will talk about that in one of the case studies later. This design has been refined over 40 years. So, I mean, at this point, I think we probably have close to 45 or 50,000 of these out in the field, all over the world. And we've really done a lot, listening to customer feedback to try to improve the performance and increase the reliability of them. So this is a cutaway of our new energized sleeve suppressor. The energized sleeve suppressor is pretty similar. It operates on the same basic principles as the bladder style suppressor, but it is kind of using a lot of different techniques. So again, the imports here and the shell, those are going to be really just there to interact with your system and to withstand the pressure. Here, all of the acoustic property manipulation is done through the actual energized sleeve. So that energized sleeve is going to be annular segments that go around a simplified diffuser. The simplified diffuser here is primarily there to retain the sleeve inside the suppressor so you don't get it shooting downstream, which is not a particularly fun cleanup day from personal experience. And it will give you some impact at like very high frequencies and like 5,000, usually outside of the region that most people are concerned with. That diffuser will very, very rarely have any kind of effect on the acoustics, but it does have some. So the energized sleeve itself is a proprietary syntactic foam that we have developed. Took about 10 years to fully develop that. So it has a urethane host matrix, and then the inclusions are going to be polymeric spheres. And these spheres are very, very, very small. They are about 20 micrometer in diameter, just to give you a little bit of kind of reference. So each bit of foam, each small chunk of foam will have millions or billions of these spheres in them. Again, discussing the characteristic acoustic impedance in terms of the bulk modulus and density. It's pretty much the same as before, except now you have to figure out what the bulk modulus of that foam is. As it turns out, a guy named Hashen in the mid 70s or early 70s figured out how to model the bulk moduluses of syntactic foams. So he came up with this equation. I've modified the kind of nomenclature just a little bit to be more specific to this application, but the bulk modulus of the foam can be found based on the host matrix bulk modulus, which is the K sub H there, the shear modulus of that host matrix, G sub H, the bulk modulus of the inclusions, which for this type of foam will actually change depending on what pressure your system's at. And it will also be dependent on the volume fraction of your inclusions inside that foam. And again, that is kind of a variable within these suppressors. And little bit simpler, again, just that, volume weighted average to get the density in that cavity. And we have developed a few different variations of this foam, which can improve the efficacy at certain pressure ranges. So these foams are kind of designed for one pressure range in mind, but they will still have an effect at any other pressure range. It's just that they might not have a real optimal effect. So for just a comparison of these two different styles of suppressors, they both have their strengths and weaknesses. So for instance, a bladder style suppressor can be really tuned for optimal performance. I will talk about that a little bit later in the case study. You can get really, really high performance out of these. And then for an energized sleeve suppressor, you're not going to be able to tune it, but it is very effective across a broad range of pressures, which is really useful for a lot of systems now that we have, like they'll kind of idle at 1,000 psi and then jump up to 3,000 psi whenever they're working, things like that. Bladder style suppressors are available with like Buna, Viton, EPR seals, so we can pretty much make that for effectively all hydraulic fluids that you might be interested in. And the energized sleeve suppressors are currently only available for what you would use a Buna for, which is still most hydraulic systems, but they also have very limited modes of failure. Bladder style suppressors will need regular but kind of minimal maintenance. I would liken it to basically checking the tire pressure on your car. It's pretty much that simple. And then the energized sleeve style suppressors are 100% maintenance free. And that makes them really optimal for submerged pump applications. Um, Bladder style suppressors, on the other hand, are really, really, truly excellent at mitigating water hammer events. So if you put them pretty close to whatever you're having, whatever's causing your water hammer, this will take away most of the energy from that water hammer. So our standard sizes are kind of targeted by line size. So the 56 series targets 3/8 to 5/8 inch line size, and we have those available in either 3,000 or 5,000 psi pressure ratings. These are approximately 7 inches long, so they're quite tiny, and they weigh just a few pounds. And the 56 series is really kind of aimed at the off-road and kind of small tractor type of applications. The 81 series is slightly larger. It's targeted for that kind of 1/2 inch to 1 inch line size. Pressure ratings again in 3,000 and 5,000 psi. Slightly longer and slightly heavier, but again, kind of targeted more on that low end. I think these have like a flow rate of approximately 32 GPM is what we usually recommend as the maximum. The 138 series targets basically the 1 inch to 2 inch line sizes, really more that 1 to 1.5 inch is where it shines. These are available in 1,000, 3,000, and 5,000 psi pressure ratings, simply because some people really need that weight savings and they don't go up to a higher pressure. These are a little bit longer, just under 9 inches, and they're also getting a little bit heavier. The 1875 suppressors target the 1.5 to 3 inch line size. The 1,000, 3,000, 5,000 PSI pressure ratings, again, saves you really big on the weight, depending on, you don't want to oversize these things dramatically. These are a bit longer at 10.5 inches, and as I said, that weight is kind of really picking up there if you're trying to use it for like a mobile application, but for a lot of static applications, it's no big deal. That 11875 or the 1875 series has a maximum flow rate of about 191 GPM, and that flow rating that we do is based on just kind of minimizing any head loss. If you are fine putting, 200 GPM through a 1 inch pipe, you can put it through our suppressor. That will not affect it. So for port options, we offer most standard sizes of SAE O-ring Boss, code 61, code 62 split flange, NPT and BSPP. As far as materials go, most of our suppressors are going to be carbon steel, but we also do offer variations in 303 stainless and 316 stainless. I'd say probably 95% of our suppressors that leave our shop go out as black oxide, but we will also do things like ENP paint and powder coat to customer specifications. All right. So moving on, I know that I've talked a lot about like just kind of how they work, but do they actually work? So this is the transmission loss
Let me throw you a
curve.
question. We got a question in the Q&A. Is there any sample testing data available to show comparison with and without the noise suppressor for the same circuit?
Yes, I'm actually going to get to that on the next two slides.
Oh, excellent. Thanks.
All right. So this is the transmission loss curve for a suppressor that used a low pressure variant of our foam. This was taken quite a while ago. I did this when I was at Georgia Tech. So what you can see is the at that kind of low pressure 1.38 megapascal, which is roughly equivalent to 200 psi, you have very high transmission loss, and the transmission loss will be the same no matter what the system is that you're installing this device on. It becomes a property of the actual device itself. So this is a highly repeatable characterization to do, whereas insertion loss is not quite as repeatable if any of you are familiar with that type of testing. And again, you can just kind of see that this was very good at the low pressures, stayed pretty good up until about, roughly roughly 1,000 psi. This would have been good based on our standard, and then the performance just really drops off. It doesn't ever go down to zero, but it just kind of converges on some low level performance when it's operating well outside of the pressure range that it was intended for. So this data was actually taken at MSOE's FPI. Um, this is basically a comparison, direct comparison of the kind of pulsation or that pressure ripple with and without the suppressor. So this is for a suppressor that used, again, a low pressure variant of our foam, and the system pressure is 1,000 psi. And you can see the peak to peak amplitude is vastly reduced. You're basically just kind of getting very low level noise in the fluid after the suppressor was installed, this blue line here. And so the actual primary purpose of that testing was to see if our high pressure variant had worked. So this data is for a high pressure variant of our foam, and it's the same suppressor. Again, red is without the suppressor installed and blue is with the suppressor installed. So you really have like a peak to peak here without the suppressor installed of roughly 100 psi, and then a peak to peak for the system with the suppressor installed being about 18 psi. So you're talking, very large reductions in the amount of energy being transmitted through the oil. Does that answer the question? I would hope. All right. Okay, so are there any other questions at this time before I get into kind of some of the applications that we're on and then some case studies?
No other questions right now.
All right, sounds good. So, industry served. We do probably the majority of our business in the elevator industry. So, if you've ever been in an elevator that's kind of relatively short, most hydraulic elevators aren't that tall, and you thought to yourself, wow, I can't really hear that or can't feel that when I'm moving, that's us. I mean, we sell directly to MEI and they redistribute our products to brands like Otis, Schneider, TKE. I guarantee you've been in an elevator that used our product and it was made quieter by our product. In the marine sector, we do quite a bit of business for fin stabilizers, but we also do business with navies, just cutting down on the hydraulic noise in their vessels. Also, we've been used on things like the water treatment plants for the nuclear aircraft carrier that the U.S. has. A lot of different things like that. We've also been used by fishermen to reduce the kind of winch noise that they were putting out when they were trying to pull in their nets or their lines. As it turns out, whales are pretty smart, and they would kind of track these boats and eat the fish before they got to the boat. So we had some fishermen install them, and basically the whales left them alone after that. In the energies and utilities kind of sector, we do a lot of suppressors into the kind of BOPs, so that's blowout preventers on oil rigs. And our suppressors are used there in the charging systems for these blowout protectors. So basically, the blowout protector will have a big bank of accumulators like hundreds and hundreds of gallons of oil for the accumulators. And basically, our suppressor is there to protect the bladders of those accumulators. We've also been used in a power plant for kind of a cooling system that they had on their turbines. Basically, they needed to mist a coolant into the turbines, and our suppressor was able to kind of make that a very controlled misting application rather than kind of having spurts. In the mobile and agricultural sectors, we do a lot of work. So we are on things like large mining trucks produced by Caterpillar. We are on wind rowers, just kind of keeping the cab quiet. And we're even on things like balers, or kind of like those kind of drag along hydraulic equipment that you'll have behind tractors on working farms. And on that baler, we were in a little bit of a different application. So primarily we're used for noise. In that application, it was used for shock. For some reason, on their return line, they had a pressure spike that was coming through and it was destroying their chillers. So they installed our $600 device and protected a $10,000, chiller unit that they had to keep replacing over and over on warranty. In the aerospace sector, we do a lot of work for test stands. That's probably the majority of what we do for aerospace, but we're also on different launch structures. And we know that we were on the NASA crawler a while back. But mostly it's going to be the test stands and those big launch structures. In the entertainment industry, we probably have the least direct communication with the end users, or end designers, I guess. But we have been used on things like the hydraulic launches for roller coasters, and we've also been used on aquariums for water handling, and we've been used in different zoos for things like elephant gates. Getting into the case studies, as you can tell, our suppressors are in a very wide range of applications, and they're often used in combination with another noise or vibration solution. Again, really big ones are going to be kind of enclosures and vibration isolation mounts. And our customers will use us to increase the safety or increase comfort, or usually both. So at Curtis Wright, a manufacturing engineer called us up, and he was basically tasked with solving a problem at an industrial press application. So this industrial press application was a big table press, and they had a fairly large hydraulic unit in a pump room about 50 to 100 feet away. And then they were running the lines from the pump room to the press. And they had previously installed things like isolation mounts and adding hose segments to that line, anything they could do to try to decrease the noise level. And that just really wasn't working well enough for them. So they contacted us and we worked with them to select a suppressor that was appropriate for their system. We ended up with a bladder style 3138-16, so that's got -16 imports just to match what he had on his system already. It's a 3138, so it's on the larger side, but not super large. It can be supported without clamps, but we do usually suggest clamps for that. And we had chosen a bladder style because he didn't really have the restrictions of not being able to have access to like nitrogen. So before installing the suppressor, his pump room was sitting around 88 decibels. His hallway was around 82 decibels, and his table press was around 80 decibels. Any of those noises are enough to where you probably should be wearing hearing protection. Um, Definitely that 88 is more problematic and probably required it by local regulations. So after they installed the suppressor, the sound level went down to about 72 decibels in the pump room. Yeah, that's on the louder side, but it's definitely not something where you need to wear hearing protection. The hallway dropped down to about 59 decibels, and the actual table press itself dropped to about 55 decibels. Those last two, they're really kind of comparable to like just a normal conversation. So definitely safe. Absolutely 100% going to be safe level of sound for humans to hear indefinitely. And we got this nice quote from him when he provided us with this data. OMG, I can't explain the difference other than several people called to ask me why the pump is not running. That's really, really why we do what we do. We want to make it to where people can't tell that their hydraulics are running.
Hey Nathan, we have a question that
Yes.
might work really well right here. What type of pumps are noise suppressors more widely used on? Gear, piston, etc. When and if used on variable displacement piston pumps, is there any interference with pump control or responses?
So probably just because like over 90% of pumps used today are piston pumps, our suppressors are used mostly on piston pumps. It will not in any way interfere with your variable displacement pumps at all. So it's basically installed just off of the pump. So right where you would start your plumbing for whatever your system is, that's where you would install it. So it doesn't really impact the responsiveness in any significant way that we've ever heard of.
Thanks, Nathan.
Right. So moving on, Quantum Marine Stabilizers is a global hydraulics company that basically services or does work for large yachts and mega yachts, kind of like the one down below. That yacht down below is the Flying Fox. It's about a 500-foot yacht. They recently called us up pretty late in the day. It was probably around 2 o'clock, and they needed a replacement part shipped to their next port. So we were able to get them that replacement part from Chicago to Cape Town, South Africa within 48 hours. It was actually kind of a fun one. But they use the HPU, they make HPUs for anything that really is going to happen on a yacht. So they do it for marine stabilizers, anchor winches, rudders, marine elevators, pretty much anything that's going to require hydraulic power. Uh, most of the HPUs in yachts and really any kind of naval vessel is going to be put in the engine room. And that then requires the hydraulic lines to be run from the engine room throughout the vessel to wherever that power is needed, because oftentimes the engine room isn't exactly where you need to have your fin stabilizers, because you're going to need to have those at the front and the back of the ship. Engine room is usually kind of midship or back of the ship. So they were unable to really reduce the noise in the staterooms to a satisfactory level, and that's because those long lines from the engine room basically radiate sound throughout the ship. Here, what the big problem was that the sound in the oil was just causing a massive vibration of the pipes that they were using, and that was then radiating sound. So they had tried things like isolation mounts, but they weren't really particularly effective. And that's because you basically can't just install an isolation mount every 2 inches and be cost effective. So we supply them with 3081, 5081, and 3138 series suppressors. Again, this is going to be kind of like our two mid sizes, and they use both bladder and energized sleeve suppressors depending on the system. And the bladder style suppressors, that's mostly for their kind of smaller systems, and those vessels are usually in port more frequently and they can be serviced more readily. The energized sleeve style suppressors that they're using are currently the larger ones for larger systems on more kind of ocean faring yachts. So their customer comfort was increased. They no longer have any kind of hydraulic whine or rumble in the staterooms, and effectively were the reason that certain ultra wealthy people can sleep well at night. Moving on to Case New Holland tractors. Recently, we were contacted by a few service technicians from Case New Holland. They were working on the New Holland Workmaster 120 and Case Farmall 115A tractors. These are very similar tractors. They use basically the same hydraulic system on them for the power steering. And the operators were reporting a really kind of annoying whine when they were doing anything with their power steering and even some of the end effectors. So we had previously been installed on Navistar trucks, and it was also for a power steering application. So we were pretty confident that we could help them. And we told them basically we couldn't help you with the engine noise, but we can help with that whine. And prior to contacting us, those service technicians had tried doing things like isolation pads, and even replacing the pump unit didn't really affect anything at all, so they called us up. We recommended a 3056 half NBT, so that's going to be our smallest size. Again, that small size is really geared towards that tractor and off-road kind of units. Oh, I should also note that this was an ES because the farmers that had brought these in usually don't have access to just a tank of nitrogen that they can charge a suppressor with. So we wanted to get them a no maintenance solution. So I'm going to play a couple of videos of just a before and after the suppressor was installed. In the before video, you're going to hear a lot of whine anytime the steering wheel is moved at all. And it will actually even drown out the engine that this guy is sitting on top of. So hopefully you can all hear that.
I can't hear it. Sorry, can't hear it.
Is anyone else having issues hearing it?
I'm not hearing it, Nathan.
All right. Unfortunately, then I don't think we're going to be, I don't know how to resolve that. Does anyone know how to resolve that through Zoom? Sorry, it's just not something I've ever run into before.
Yeah, I'm not sure how to resolve that, to be honest with you, Nathan. Not
All
sure.
right. Well, I can just, I guess, then describe what was going on in these. All right. So basically, in that before, you had a very kind of powerful whine that was even drowning out the diesel engine, and it kind of increased when he closer to full right or full left on his power steering. And then in the after video, you really don't hear the power steering at all until you get very, very close to that full left or full right. But you will hear the diesel engine, and even that diesel engine kind of overpowers the whine a bit on that. I can look at getting these two videos onto YouTube and providing the hosts. So I can provide a link to Pete and Paul, and we can distribute that video that way.
That sounds good. Thanks, Nathan.
Yep. All right. So are there any questions?
I don't see any questions. Oh, here it comes.
Right.
What are the downsides of suppressors on pumps?
The downside of suppressor on pumps, really the only one I can think of is that you're going to increase the weight of your whole system. They don't really impact the pump whatsoever, but the whole system will be slightly heavier. That's the only kind of downside that I can think of.
Okay, thank you, Nathan. I don't see any other
Thank you,
questions.
Nathan. Very
Right.
interesting presentation.
All right.
All right. I'm happy to introduce Shenmukh Shrode. He's from Parker Hannifin. He's an electrification engineer there, and he's going to talk on towards quieter hydraulic pump technologies. I've been following his work for many years, and I'm excited about his presentation. Shenmukh Shrode, PhD, has over 5 years of experience in the design and manufacturing of hydraulic pumps and e-pumps. He currently serves as an R&D engineer at the Parker Hannifin Motion Technology Center, focusing on new product development to expand Parker's e-pump portfolio. So with that, Shenmukh, I look
Thank
forward
you,
to
Paul.
your presentation.
Thank you, Paul, for the great introduction, and I hope you can see the screen and you can hear me well.
Yes, very good.
Okay. So yeah, thank you for the introduction, and like few of my previous panelists mentioned, hydraulic pump is the heart of the hydraulics fluid power systems that are widely used in a lot of applications, and the noisiest component is the hydraulic pump. So a lot of noise reduction or noise mitigation revolves around hydraulic pump technologies. So here, today's presentation, I want to address how Parker is thinking of re-engineering these hydraulic pump technologies to address growing mandates around noise and also trends in electrification. So agenda for my today's presentation, brief introduction on the noise in hydraulic systems. I'll take the liberty of being the last panelist. So a lot of the aspects were already covered by Sudhir and Nathan. I would jump to noise in hydraulic pumps. What are the key sources that we tackle in hydraulic pump design in order to reduce noise? And then I would take the opportunity to present two case studies that we did on a bent axis piston pump and a vane pump to make the next generation or noise optimized E-ready pumps. And both these case studies these products were launched fairly recently. But I would also like to take the opportunity to present the ongoing trends that Parker is acting on in hydraulic pump design and present it to the audience to sort of get a realignment or any feedback. And such a feedback is important for our integral new product development process, so that we end up improving our product portfolio and providing better products to support the needs of our customers. Like Sudhir and Nathan also very rightly mentioned, we classified the noise sources in hydraulic systems in three broad categories: fluid-borne noise, structure-borne noise, and airborne noise, depending on the media that they propagate through. But noise in electrified hydraulic systems, there are several other challenges. One interesting thing about noise is the right level of noise is very market and application environment dependent. There are growing city mandates, government regulations around noise that equipment should be operating under, but also an important aspect is the operator comfort, or like Nathan pointed out, sustained exposure to noise levels can have very serious impacts on the operators as well. And one of the most important issue that Parker or today we are seeing is most of the hydraulic pumps out in the market were designed for internal combustion engine operation. And the engines being so loud, there was little focus on the NVH of the hydraulic pump itself. Or I would say that the focus on hydraulic pump design when we are phasing out from the diesel engine has increased so much. And that is because the electric motor, which is now the prime mover in electrified systems, is very quiet. And that leaves the hydraulics to be the noisiest component on the machine. And with this points to the need of new product development in hydraulic pump technologies hydraulic pump technologies in general. Within the pump itself, there are several fundamental causes of this noise being generated. The first and the foremost is the noise coming from fluid sources due to the pressure pulsations coming from the displacing actions of different hydraulic pump technologies. The way this fluid is transported within the pump technologies can result in turbulence, cavitation that can also have impact on noise. As Sudhir briefly mentioned, all these also translate to mechanical sources, or they actuate the structure, and therefore the structural response of the entire pump body or the moving parts that are supported by several lubricating films in the hydraulic pump also can cause noise during hydraulic pump operation. And the last aspect is more miscellaneous: how the pump is mounted, the operating conditions, the resonance of the system that it is mounted in, any abrupt operating condition change or change in loads can also translate into hydraulic pump noise. And depending on the different pump technologies, the operating limits, and the fundamental displacement actions, there is a wide spectrum of hydraulic pump technologies that are available for users in today's market. Note that all these technologies are quieter than the diesel engine, which I have on the most extreme right of this chart. When we think of efficiency, these hydraulic pump technologies also follow a very interesting pattern. They are way efficient than the diesel engine in general. But one thing to note is that the most efficient hydraulic pump technologies, the piston pump and the bent axis, also tend to be the most noisiest ones. And especially when we think of electrified systems, the electric motor has a very interesting placement in these charts, is because it is also the least noisy, and it is the most efficient one in the entire spectrum of noise and efficiency when we think about our power units that power our fluid power systems in current operation. And with electrification having a broader impact beyond noise in terms of lower emissions and ability to operate more efficiently from cleaner sources of fluid, beyond the hydraulic product portfolio of Parker, which is the bread and butter for Parker Hannifin Corporation. Here I also want to present the electrification focused portfolio. To name a few, this is the global vehicle motor, the GVM, which is widely used in OEMs. To drive the motor, we have the global vehicle inverter. But the electrification efforts at Parker do not stop at just motors and inverters. A lot has to change on the pumps that these prime movers drive. And these pump technologies are these future pump technologies, or the product developed are based on configured e-pumps and integrated e-pumps based on our e-ready pump portfolios. And in the next few slides, I would be going in details of what I mean by e-ready, but I want to pause here for a minute to see if there are any questions from the audience.
No questions at this time.
Okay, thank you. So the first case study to demonstrate what is e-ready revolves around the bent axis piston pumps. Bent axis piston pumps, the F12 and the F1, are widely used in applications where high pressure ratings are required due to their numerous advantages compared to other hydraulic pump technologies. But when we think of electrification or any changing market trends, we identify several bottlenecks that limit our bent axis piston pump technologies. And one of the bottlenecks that I briefly mentioned on the noise spectrum was that these bent axis piston pump technologies are the most efficient ones, are also the most noisy ones. So that these pump technologies therefore make a good case for improving or re-engineering. And here are some bottlenecks that we identified or modified when we made these existing F12, F1 pump technologies to e-ready pumps. And what e-ready essentially means in this case is we worked on the noise reduction of these units. They are at least 5 to 6 dB quieter than their predecessors, as well as an increase in self-priming speed of these hydraulic pump technologies. And these pumps, the new E-Ready pumps, were launched last year in 2024. And this is sort of a good example of how noise has become an integral part of new product development in hydraulic pumps in today's world, and as well as in Parker. How we achieve this noise optimized design in the bent axis pump itself. As we heard earlier, that the fluid borne noise is also a very critical aspect. So here I want to demonstrate 3 different design aspects that we improved on. Firstly, we smoothened the flow paths in the flow in the ports of the hydraulic pumps using 3D CFD software. Here we are showing some results from Cimerix. Again, because the increase in self-priming speed was also a motivation that has to be tied with, and to avoid any cavitation when operating at higher speeds, in order to ensure that the piston bores or the displacement chambers are completely filled during the motion. And the most important aspect for noise being the port plate, which decides the pressurization timing of the displacement chambers as they pressurize the fluid. The other important aspect is also to think on how the structural aspect or the housing of the pump responds to the fluid dynamic phenomena happening inside the hydraulic pump unit. So here we use sound transfer path analysis and the structural responses to optimize the structure of the hydraulic unit itself. And a similar methodology can then be applied to swash plate type piston pumps that applies to our P1M product line. The next case study I would like to present is the vane pump. The vane pump in general is also inherently a low noise pump when we think of the noise spectrum in hydraulic pumps that I showed a few slides before. This E-Ready vane pump was also launched in 2024, and what we were able to achieve was a much smaller cartridge, and this was possible by optimizing the fluid passages in the pressurizing displacement chambers and some redesign in the ports. This enables us to downsize or reduce the weight of the pump in itself. But what it also helps is this new E-Ready T8 mini pump technology is 4 to 5 dB lower in noise as compared to its predecessor, the T7. Here I show a noise level measurement at 2000 RPM for a range of pressures on the x-axis. Beyond the lower noise operation, an important aspect of this product development was to increase the self-priming speed of these units. And the T8 Mini has a self-priming speed of 5000 RPM. And these are speeds that the electric motor usually prefers to operate at. So with the hydraulic pump now matching the preferred speeds of electric motors, it is possible to downsize the electric motor, the electric inverter, in order to meet the same flow and pressure requirement from the application. This not only results in a compact e-pump, but also is a very cost-effective solution. The other important aspect is also this being much quieter, given that the hydraulic noise is reduced even further. Coming back to the noise spectrum for the hydraulic pump technologies, one other important recent development or recently growing market is for helical pump, gear pump technologies. These pump technologies present a very unique advantage is that during the pressurization, the dead volume is very minimum, or say near to zero. What this allows the pump to do is during its operation, the ripples that the pump generates due to its pressurization action is much lower. And these low ripples then translate to lower noise to lower noise perceived by the receiver in general. So here I also want to take the opportunity to realign with the audience. Nathan also pointed this out, that 90% of the market today is high pressure piston pumps, mainly due to their ability to operate at high pressure very efficiently, their ability to vary its displacement, resulting into better flow control technologies. But the downside is noise. But so here it's an open question to the audience. With the noise mandates and the noise being more and more important, do we think the market would shift to more low noise pump technologies? And so here I also want to pause for any questions before I present, what are the trends that Parker is acting on when we are designing new products for our hydraulic pump and motor market.
Shanmugh, I don't see any questions right now, but I have one a little bit. We've also noticed NFPA collects data on components and on a monthly basis, and we noticed kind of a steady decline in vane pumps. And is it something about the pump itself, or about the markets that the vane pumps are used in? Are there specific areas that they tend to be used where maybe some of these issues aren't as critical, or what's a good understanding of that?
So just to confirm, you mean the vane pump? From NFPA's data, you think vane pumps are on a decline?
That's what we've seen. It seems like there's
okay.
Fewer companies that either make them or report the information on them, and we see that a movement, like you said, maybe more towards piston pumps and so forth.
Yeah, but this would be very contradictory to what we think at Parker. You see, we are even today we are developing newer vane pump technologies, and mostly to address the noise issue. Because if you see in the spectrum, this spectrum is based on extensive testing that Parker did in-house on their components, also feedback that we receive from OEMs. The vane pump technology from Parker and previously from Denison is one of the low noise pump technology. So we still see development happening in vane pump, and with the E-ready pumps and the T8 Mini being able to reach high self-priming speeds, we expect this market to be favorable, especially when thinking of electrified systems.
Thank you. That'll be interesting to watch as we go forward and see how that might change.
Yeah. Yeah, and I feel the OEMs or the vehicle manufacturers obviously will have a better perspective on this, trends, because they obviously study their systems with different flow sources. So this could be something that, would be interesting to know from our customers or people in the audience as well. But with that, I would like to also discuss, the market trends that we have been hearing, or what is motivating Parker to develop newer pump product technologies. The first interesting aspect is that the electric motor now has speed variability in it. So in order to achieve flow control with an electrified in an electric motor driven fluid power system, it is possible to swap out the piston pumps to cheaper hydraulic pumps and also low noise pump options, and cheaper as in cost effective compared to the piston pumps. The other development that we see are high speed pumps. So here I sort of have a short comparison to meet a pressure and flow demand. If I have a 3000 RPM unit that is typical of an engine operated system, I would need an electric or a prime mover for 112 Newton meter if I want to swap out the prime mover to an electric motor. But with high speed pumps, this torque can be reduced to 67 Newton meter. And because the size as well as the cost of the electric motor is directly proportional to the torque, we see that matching the self-priming speed with the high-speed operation of the electric motor has serious downsizing and cost-saving potentials. The other aspect on variable displacement pumps, where piston pumps can continue their dominance, is that with the variability in the electric machine and the variable displacement pump, they can be combined together to optimize for noise as well as efficiency. So in order to meet a particular pressure flow demand with this combination, we would have a different set of operating speeds and the displacement of the pump. And we can write an e-pump control algorithm that can allow to operate at the least possible noise level throughout the operation, depending on the operating condition. And again, for the structural aspects, vibration isolations or encapsulations and mounting recommendations are also required to be thoroughly studied to reduce the noise level. With that, I want to point out that all these new product development initiatives are that Parker is focused on today for electrification or noise is based on the feedback that we receive from talking with our customers. And therefore, I welcome any feedback so that Parker can utilize its fluid power expertise to provide improved parts to our customers in the future. And if required, I have my email address here. You can reach out to me, but that is all I had today. Thank you for your attention, and I'm open to any questions.
Thank you, Shanmukh. I don't see any questions unless anybody's putting them in, looking in the chat as well.
Shanmukh, I have got a question for you.
Yeah, go ahead.
Paul from MSOE. Just curious about, we know that these products are all used or many of them are used in industrial applications that are already operating in with electric motors. And I was wondering if you could explain to me why in this application where we're operating outdoors, the noise control seems to be more important than, if you will, in an industrial setting like a factory. Or what are the difference in priorities, if you would?
Right. And yeah, noise control, I feel like even in a closed environment is as important. It's not like less important, but it is easier to implement noise suppression mechanism in an industrial environment in the room that the equipments are operating at, beyond the source of the noise. But doing that in a machine is very challenging, or in the cabin of a off-road machine is very challenging. And that is where the focus on the source of noise becomes more and more important. But I agree with you, even before this electrified or any system, noise was important and is important in industrial pumps as well. And therefore, a lot of the industrial pumps that Parker makes has noise mitigation features that tend to increase the footprint of the pump. So it is slightly bulky, but the industrial market segment has the leeway or has the flexibility to allow for a slightly bulkier product footprint at the advantage of noise mitigation. But on a mobile machine, increasing the footprint has severe disadvantages in terms of installation challenges, and making the structure smaller as well as wanting to have a low noise pump, that's where it gets a bit challenging. This is just my thought.
Mm-hmm. That makes sense. That's a good explanation. I have a perception, I could be wrong, but a perception that vane pumps generally cannot achieve the high pressures that are seen in other pumps, piston pumps and bent axis pumps in general. Is that correct?
Yeah, I would say it is correct. But in general, like the newest vane pump technology is able to reach 280 bar rated operation and 300 bar max pressure operation. So that is already competing with, say, medium pressure open circuit piston pump technologies. So again, I agree the piston pumps can go to 350 bar, 400 bar, but at least the medium pressure technologies, the advancement in vane pump technologies is able to compete with that market segment of the piston pumps and with lower costs.
Yeah, it's very impressive the way that you can make that package half the weight.
Right. Yeah.
And achieve the same performance. That's very impressive and reduce noise.
Yeah. Thank you.
Yeah, we have another question. Have you studied the effects of pump timing on hydraulic noise?
So pump timing. So is this more on the port plate timing, or just to make sure I understand the question right?
It doesn't specify unless the person puts something more in there. Oh, no, it's a different question. So no specification on that. Have you studied the effects of pump timing on hydraulic noise? Drive gear timing, he says.
Drive gear timing. Yeah, I don't quite understand the question here, but so I don't want to, make up an answer, but we do consider the pressurization timing of each, plotting the displacement chamber over a complete shaft revolution, and then thinking what is the electric motor shaft at, where the GVI is driving the electric motor shaft. So we do consider a lot of that e-pump operation related subtleties in the coupling that can generate noise, but I'm not quite sure what timing here is referring to.
Okay. Another question. How do the vane pumps compare to gear pumps with similar operating conditions longevity-wise?
Yeah, that's a great question. The gear pumps are very robust. They can handle contamination levels way higher than the vane pumps. So definitely there are advantages of gear pumps in general, but what we noticed, especially in the gear pump, the external gear pump technologies, that is one of the more cost-effective solution, is that it tends to be noisier than the vane pump technologies. Obviously, there are gear pump technologies such as the internal gear or the helical gear pump technologies that are quieter than the vane pump technologies, but they tend to be more expensive. In terms of longevity, the external spur gear definitely has an advantage over vane pump technologies in terms of robustness and handling contaminants. But yeah, compared to the other low noise gear pump options, I feel the vane pump is at par in terms of longevity. That's what we hear from customers, unless, there are some tests that some of our customers have done and are wanting to point us to, a different direction. Because we have both these gear and vein pump technologies in our portfolios, and all of our pump teams are looking to improve our products.
Okay, thank you, Shamak. I do not see any other questions right now.
Okay. Yeah, thank you so much.
Thank you.
Yeah, bye.
Paul, off to you.
Well, I want to thank our speakers, Sudhir and Shamak and Stefan and Nathan. Appreciate your presentations. I learned a great deal from your talks, and I'm sure our audience did as well. If anybody wants to receive CEUs for participating in this training session or this FPIC webinar, please reach out to me and I'll send you a certificate. And again, I just want to thank our speakers for the excellent presentations that they gave our FPIC and NFPA members today.